Hi everyone, and welcome to Eric's Electronics Workbench. So today on the bench I have this Leader LBO-51MA XY display. I found this one in unknown working condition, but it looks super clean, so let's see what it takes to get it up and running. Now this type of display is handy to have for various uses, and it should work with the HP 5182A waveform recorder generator I covered in a video a while back. So the 5182A is meant to directly drive an XY display. Now many oscilloscopes have an XY display mode, and I've shown how to use that feature in other videos, but I've wanted a dedicated XY display to save the wear and tear on oscilloscopes when only the XY display function is needed. Now usually these displays are just called an XY display, but they're actually an XYZ display, as the third input, Z, is the intensity control, or referred to as the blanking control. So the first thing I noticed is the voltage rating tag on the back. It's marked 240 volts 50-60 Hertz. So I need to open it up and see how to determine if the voltage is actually set for 240 volts. So I'm in North America, and the normal line voltage is 120 volts, so it's unusual to operate a device like this on 240 volts. And I purchased this from a seller in the US. Now there's no external voltage selector switch, although the back panel is punched and marked for such a switch. So let's take a look at the fuse rating. There's two different possible fuses depending on the line voltage. So 90 to 132 volts is supposed to be 0.8 amps or 800 milliamps, and then 180 to 250 volts is 0.4 amps or 400 milliamps. So let's see what's actually installed. There we go. And it's a pretty small little fuse, 250 volts, 400 milliamps. So yep, 400 milliamps, that's the higher voltage rating. So I imagine it, at least it was factory configured this way with 240 volts. But again, I don't know if it's been reconfigured to the lower voltage or not, so let's find out. Wow, super clean inside. So it's clean on the outside and clean on the inside. Looks fantastic. So I don't know exactly what year this would have been manufactured, but there is no dust whatsoever. So very, very nice inside. Let me get this top cover set over here, and let's take a closer look at the AC line coming in, which is in this back corner here. So, transformer, so traditional linear type power supplies in here, not a switch mode supply. So it looks like down here there's an AC line filter, AC power connector, and then there's a blue, brown, and green wire. So the green is the chassis ground, blue is going to be neutral, and the black is the hot. So the black wire is going over to the fuse holder, and then off of the fuse holder it comes over here. Let's see, it's going up. Where is it going around here? Wraps over this way. Oh, it goes over to the switch. Okay, makes sense. So then this brown wire must be coming back from the switch. Okay, gotcha here. So that means the brown wire comes over to this tap, but we can see there's other taps on that transformer. And if I have a better view, yes, they are marked. Perfect. So that's going to make things a lot easier. So it looks like, this is really awkward to see down in there with the camera. Let me get the camera positioned a little bit better, and you can see down in here. We'll take a look at those taps. All right, so it looks like the transformer has two primary windings. It starts over here at the bottom end of this winding. It's marked as 0. Then the next tap is 100, and then the next tap is 120. Then it repeats again. It's 0, 100, and 120. So if you're going to operate this on 240 volts, those windings would be in series, and if you're going to operate on 120 volts, they would be in parallel. So just following the wires, it comes off of the fuse holder, goes over to the power switch, and it goes off of the AC line filter, it goes over to the power switch. So they're switching both sides of the AC line, then it returns back on this brown and blue wire from the power switch and comes up to the transformer. So it's over here on this blue wire, and that's going to this tap, which is 0, so the bottom end of the winding. And then the 120 volt tap on this first winding is going right over here to the bottom end of the next winding. So they are in series. And then the far end over here, 120, is the brown wire, and then that's returning back, that's on the AC line. So yes, this, being in series means that it is set up for the 240 volts, so it must have left the factory this way. Again, interesting that it's being sold in the US, and this is not a standard line voltage that you would find here. So either custom made, maybe a special order, or maybe this was originally sold overseas and then was brought back to the US. Hard to say at this point. So I need to reconfigure these wires over here. Just move these jumpers around and put both of the windings in parallel. All right, so I changed the wiring on the transformer over to 120 volts. So you can see on the before and after photos and the difference on that wiring. By the way, notice on the CRT, there's this metal shield, but there's no deflection coils on the neck of the CRT. And that's because this is an electrostatic deflection type of CRT, meaning that the electron beam is deflected on the X and Y axis by plates that are inside the CRT. So again, it's electrostatic deflection, not magnetic deflection. And of course, this is a high voltage anode. So be very careful if you're working on a device like this. There's thousands and thousands of volts on that anode. And if you unplug this wire, then the anode itself can retain a charge, so you have to safely discharge it if you were to work on the CRT. So if you're following along and you're working on a device like this, you're definitely doing so at your own risk. Take care and be safe, especially around the high voltage and AC line powered devices. All right, so let's get this powered up and see if it works. So grab the power cord, get this plugged into my current limited isolation transformer and variac. Now I'm just going to start at 120 volts. I'm not going to bring the voltage up slowly. But it is current limited with a 70-watt incandescent lamp that's in series with an AC line. And I did change this fuse to the larger rating as well. All right, so I'll get this turned a little bit here so you can see the front. And I'll monitor the amperage and wattage that's on the variac meters just to make sure everything looks okay. All right, so here we go. Looks okay, no problems. Power light is on, that's good. Doesn't seem to be anything. Oh, there it is. Perfect, look at that, there's a dot. Excellent. So with these XY displays, you definitely don't want that dot to be a really high intensity, and not moving. You could end up burning the phosphor. Yeah, focus control seems to work. And let's try, yes, it does move it. Check it out. How cool is that? Excellent. Seems to be working at least on the first power up. So let me get some signals connected into here, and we'll try some different test signals and patterns that'll come up on the display and see if it responds correctly on the X and Y axis and the Z axis as well. All right, so there's some switches and calibration pots on this XY preamp board. Now there's a shield right in the middle, and it looks symmetrical from side to side, so I would imagine that the X and Y axis amplifiers are identical. And in fact, it looks like you could divide this connector right in half, and these wires that are color-coded coming over here to these control pots, this is the X-axis, and this is the Y-axis. So if we come over here, I would imagine that this is the X-axis amplifier, and this is the Y-axis amplifier. I'm not going to touch the calibration pots unless something that seems to be wildly out of spec. But starting with these switches, this switch is coupling, so it's AC or DC, and it's in the DC setting, so direct coupled. That's fine, I would want that. And same with the switch down here, it's on the DC setting. This switch says invert and normal, and this is invert and normal. And both switches are on the invert position. I would actually think maybe they should be on normal. I'm not entirely sure, but I'm going to go ahead and move them down to normal, like that. At least we'll start with that and see how it functions. Right, so I noticed something. This actually isn't a pinpoint dot, it's a short horizontal line. It's on the X-axis, which means that the X-axis is being deflected just a little bit. And it doesn't seem to have any problems on the Y-axis. Again, it's only related to the X-axis. And I noticed that it was doing this when it was powered off the isolation transformer, which means that the chassis is floating. I thought, well, maybe it was picking up some noise and interference. There's fluorescent lighting and LED lighting around the bench, and all of that is electrically noisy. So now it's powered right off the AC line as it would normally be used, which means that the chassis is earth grounded, but it's still doing it. And then I thought, well, maybe because the top cover was removed and the cover is metal and that would add shielding, so I installed the top cover and it didn't change anything. It still had the same amount of deflection. So the cover is removed again, but it had no effect. Then I noticed that this gain adjustment on the X-axis is turned all the way to the maximum, so it's full clockwise. And if I go counterclockwise and turn the gain down, take a look at that. Now it is a pinpoint dot. But of course it should work with the gain turned all the way up, like that. Now the gain on the y-axis is also at its maximum, and if I turn it down, it doesn't change anything. You know, there's no signal, so we're not really seeing any change at all, and it doesn't, you know, change the deflection or anything on the y-axis. So I thought, well, why is it picking up this noise or interference or something that's causing some deflection on the x-axis? So I started looking around inside the instrument. Get this moved up here a little bit. And way in the back here is the back panel and the BNC connector for the x-axis input and the other connectors on the back. But this x-axis input is very close to the transformer wiring right here. And take a look at this. If I just get the focus touched up to the front again, if I press down on this brown wire that's on the transformer, so that's the hot AC line, it starts to make this have less deflection. It becomes more of a pinpoint dot. So what I need to do is move this wiring down away from this BNC connector, because right on the back of the BNC connector it's not shielded, but it is a shielded cable, you know, once it's connected and runs off of the BNC. So this definitely needs to have the wiring rerouted and moved down because it's way too close to that BNC connector. So let me reposition that and see if it takes care of this problem. But it definitely looks like it's picking up some noise and interference, you know, 60 hertz hum basically. And it's very, very sensitive on the input. And the input is high impedance, and of course it's floating right now. And you know, it's just making it pick up that noise. So I'll reposition the wiring. Let's see what happens. Right, so I repositioned the wiring coming off of the transformer terminals on the primary side, just bent them down at a 90-degree angle so it's well away from that BNC connector, and it's much improved. Check it out, it's a very sharp dot, and the gain is at the maximum, but if I turn it all the way from maximum down to minimum, it remains a very sharp dot in the whole range. So that looks like it's working correctly now. So this XY display has the blue filter plate installed, so there are no graticule lines. There was a graticule plate optionally available with the standard 10 divisions for X and 8 divisions for Y. So the X and Y input range is 50 to 150 millivolts per division, DC to 3 megahertz, although the inputs can withstand up to 100 volts DC plus AC peak. So the full-scale deflection for the X-axis is 500 millivolts to 1.5 volts, and for Y it's 400 millivolts to 1.2 volts. So taking a look at the block diagram, we can see the three inputs go to the respective amplifiers. The X and Y amplifiers are then driving the X and Y deflection plates in the CRT. So any movement of the CRT dot is dependent on the X and Y inputs, and the Z input for blanking. There's no sweep or time base or any type of triggering like an oscilloscope has. So the remainder of the circuitry is basically low and high voltage power supplies. So the anode voltage is generated from the high frequency oscillator, which feeds a multiplier to create the 5000 volts DC. There's also a CRT heater voltage which isn't shown, but it's 6.3 volts AC taken from the power transformer secondary. By the way, I was looking for the service manual and schematics, and I contacted Leader through their website. They replied within a day and said that this was an obsolete device, but that they were checking. Then the following day, another email saying they found the service manual on an old hard drive, and they sent me the PDF. So that's pretty awesome to receive such assistance from a company regarding obsolete equipment. All right, let's see what happens with some input signals. So I have the two-channel function generator connected to the X and Y on the display. It's off at the moment, but each output will be a sine wave. So channel 1 is on X and channel 2 is on Y. So if I turn on just channel 1, or the X input on the display, so it's on a half a hertz sine wave, so very low frequency, and you can see the dot is just tracking that sine wave. So the amplitude is 500 millivolts peak to peak, or half a volt, and it is deflecting all the way side to side, so that's perfect. And if I change the gain, so the gain is at maximum right now. If I turn the gain down, yep, just moves a little bit. Now if I increase the frequency, let's say something like 100 hertz, turn up the intensity a little bit, and it just looks like a solid line at that point, because the persistence of vision, it just, your eye can't track, something that's moving at 100 hertz like that. But if I go back to low frequency, right there. Okay, so I'll turn that off and I'll turn on channel 2, so that's the Y. So it's just on the vertical axis now. So perfect, also a half hertz. And it's going full peak to peak, and let me check that. Yep, that's 400 millivolts peak to peak, so it's going full scale. If I change this gain, turn that down, yep, just moves a little bit in the middle, perfect. So now if I turn on both channel 1 and channel 2, so the sine waves are in phase. The phase is just set at 0 on the function generator. So when they're the same frequency in phase, then you end up getting that diagonal line. And if I change the phase, so I'll go to 90 degrees, well, it ends up tracing out a circle. So now if I increase the frequency, let's go over here, make this 100 hertz, and we'll go back to the other channel and make that 100 hertz. And there we go. So again, it's just the persistence for vision. It ends up looking like a solid circle instead of just the dot moving around. So excellent. So I've shown the idea of using an XY display if you're comparing two different frequencies in some other videos, but I was using the XY feature on an oscilloscope. So I had a 10 megahertz signal going in from my GPS disciplined oscillator, and then I had a 10 megahertz signal that was from an ovenized crystal oscillator, and I was adjusting that ovenized crystal oscillator to exactly 10 megahertz. And you know they're at the exact same frequency when the pattern on the display is no longer changing. So that's one way that you can use an XY display. All right, so now on the function generator, the phase is set back to 0 degrees, but the X input on the display is 100 hertz. The Y input is 100.1 hertz. So when the frequencies are different, then the pattern shifts around and changes. So instead of 100.1 hertz, if I lower that back down to exactly 100 hertz, it's back to the horizontal line. And if I go just a few steps up, try this right here. There we go. So now that's 100.02 hertz. So very slight difference in frequencies, and the pattern just changes very slowly. If I go like this. So now there's 200.1 hertz and 100 hertz on the x-axis. But again, y-axis is 200.1, so you get a little bit different pattern. And if I change that, there's another pattern. So almost infinite number of patterns that you can end up creating depending on the frequencies. So again, X is at 100 hertz, and now Y is at 400.3 hertz. And with the function generator's arbitrary waveform generator, you can get some pretty interesting looking results. Alright, so check it out. The LBO-51MA display is working perfect with the HP5182A waveform recorder generator. So this waveform that you see displayed up here is the signal that's coming from my function generator on this coax. So if I disconnect it, you'll see that the signal will disappear. So that's a real-time signal of what's being applied to the recorder generator. So this is digitizing the signal, and then it can store it. It can also replay the signal back out as a generator. And then this is creating the X, Y, Z signals that are going up to this display. So if I go over here to this display calibration, that's a test pattern to set up the display. And of course it needed some adjustment initially, but it looks great, no problems. It was able to dial it right in. And if I go over here to this arm setting, so shift and then arm delay. So I go all the way down here to arm delay 7 milliseconds. Puts that display up there, so it's able to drive the display correctly and create that text. So it looks very good. Alright, so it looks like the Leader LBO-51MA is working well, and it's time to find it a permanent place on the bench. So if you enjoyed this video, you can let me know by giving it a thumbs up. And don't forget to subscribe. There are many projects lined up and you won't want to miss seeing them. So thanks for stopping by and taking time to watch. See you next time. Goodbye for now.